Swayam Prabha. Digital India. Educated India.
We have quite extensively analyzed the response of a first order circuit to constant inputs. So now for any arbitrary first order circuit and some piecewise constant input, you can find the response. It's quite hard to find the response for some arbitrary time dependent signal. So we have started with something that's constant. Now we'll go to something that's a little more complicated. So let's say we have, again, I'll first take this circuit, the same thing that we have been using. In this case, I will use an exponential as the input. Okay. There are a few reasons for using this. You will find that any input can be decomposed into a sum of exponentials or an integral of exponentials with different values of this s. Okay. So we won't get into that.
You can assume that for now you will see the details in a course like networks and systems.
And you can for now imagine that maybe you had a first order system, it gave some exponential output and you fed that into another first order system. That's why we study this. Okay. What happens if we do that? Okay. So that's the motivation to do something like this. In this case, if we write out the differential equation, we will get okay. So we have to find the value of Vc which will satisfy this, and we assume that we solve this for t greater than 0 and then so on. Okay. So how would we go about solving for this? So there is something known as an integrating factor, which is basically essentially solutions that you have mugged up based on previous experience. So you know that if the input is of this function, the solution will be of that. Okay. Let's do the simple minded thing like we always do in this course, which is that this I know how to solve. Okay, I'll try to reduce this also to that. That's how I solved the constant also, right? With the constant input, I will change the variable. So let's try to do that. First, the simple thing to try to do is okay. So please rewrite this in terms of Vc1
and compare it to what I derive. We get Rc dVc1 by dt plus Vc1 equals minus SCR Vp exponential St.
Okay, the simplest thing didn't work. We didn't get a homogeneous equation. So what do we do?
We can try a linear combination of these two equations.
This multiply by SCR and this multiply by 1. Okay. What we get is Rc right, because it's a linear operator, right? I put this inside the derivative and then here also I get also on the right hand side 0. Okay. So now this new variable, you could call this Vc2 if you want. What is the solution to Vc2? Rc dVc2 by dt plus Vc2 is 0. Vc2 is some constant times exponential minus t by Rc. So now from this find the solution for Vc, which is what I want. Okay, just back substitute all the variables and find it only in terms of Vc. Please do that. Just clear? Just some silly algebraic tricks to get the right hand side to be 0. That's all. Okay. What is the solution?
Vc20 exponential minus t by Rc equals SCR times Vc plus Vc1.
This Vc1 itself is nothing but Okay. So what do we have?
Vc of t equals Vp exponential St plus Vc20 exponential minus t by Rc divided by SCR plus 1.
Okay. Now you can express this slightly differently also. So this Vc20, I mean Vc2 itself doesn't have any particular significance except that it was an intermediate variable that we got while solving this, right? So this is some constant. So you can also simply write this as Vp exponential St by SCR plus 1 plus some constant times exponential minus t by Rc. As usual, whether you put it like this or like that, this constant has to be found from initial conditions. Okay. So let's say you know that the capacitor voltage is some value at t equal to 0. You substitute t equal to 0 in this whole thing and then find that thing. Okay. So I will simply say some V naught or something like this. So this has to be found from initial conditions. Okay. You can put it this way or this way. This is just a redefinition of the constant. What I want to point out here is, what is this part of the response? Steady state response or forced response or the particular solution. Okay. And this is the natural response. The natural response of the circuit remains the same always, right? Only thing is its coefficient will change. By the way, this coefficient will also depend on what forcing input you apply. This is known as the forcing function, because if you substitute Vc of 0 equal to some value, that will also depend on S. To adjust this value of V naught, some S will come in somewhere. Okay. For instance, if Vc of 0 was 0, I would get Vp exponential 0, which is just Vp. Okay. And this value of Vc20 would be minus Vp to make it equal to 0. So this constant would be Vp divided by 1 plus SCR. Okay. So this constant itself will depend on the input that you apply. It's not the same for any input, and for 0 input it will be different also. For 0 input, that will simply be the initial voltage on the capacitor. So it will depend on the initial voltage on the capacitor and also on the forcing function. Okay. So the natural response does depend on the input. Okay. The steady state response depends only on the input. That's the definition of the steady state response. Okay. Now for any stable circuit like the one we have, this natural response will die out with time and you will be left with only the steady state response. Okay. Is this fine? So this solution is clearly not valid when 1 plus SCR is 0, right? Okay. So you tell me what might happen. But you do get an interesting solution. What you can do is, you take the limit as 1 plus SCR tends to 0. Convenient way of doing it is, let's say you define yet another variable, some delta equals 1 plus SCR. Okay. And then everywhere you have S, you substitute it by the appropriate mapping with delta. Okay. And then you take this limit. Very simple stuff. You have to use limits and L'Hopital rule and you will get the answer. Okay. So clearly this as it stands is not valid when S equals minus 1 by CR, right? What does that mean? What is that condition? SCR plus 1 equal to 0. So what it means is, if you excite an RC circuit with an exponential which is the same as the natural response of the RC circuit, you will get something weird. Okay. So that's the bottom line, isn't it? SCR plus 1 equals 0, that means that this forcing function is Vp exponential minus t by Rc. Exponential minus t by Rc is also the natural response of this system. So when you excite an RC circuit, in general any circuit, with an exponential which is also the same as the natural response, you will get a slightly different solution. Okay, you can find the solution. So you have the steady state or forced response and the natural response that you always have. What is a very, very important thing is that if the input is an exponential st, the forced response is also an exponential. Okay, isn't it? What is the forced response? This whole thing is some constant. Okay, we applied Vp times exponential st. What we are getting is some other constant Vp by SCR plus 1. Maybe it is slightly smaller than Vp. But the point is, if you have exponential st as the forcing function, the steady state response is also exponential st. Okay. So, it is a very, very important feature of any linear system. So, these complex exponentials are eigenvectors of these linear systems. Eigenvectors I explained briefly. What it means is that if you transform a vector in some way, let us say using a matrix, you will get another vector. Now, eigenvectors of a matrix are those vectors for which the transformation is only in the magnitude, not in the direction. Similarly, here, if you have exponential st, only its magnitude is manipulated. I mean, it has not become some other function. Okay.
A course like networks and systems will be based on,
or at least a big part of it will be based on this exponential st being an eigenvector of this. Okay. So, that is why it is very, very useful. So, combining this idea that the force response to exponential st is a exponential st, and you can decompose any input in terms of exponential st. Okay. You know that a square wave is a sum of sine wave and its harmonics, right, at the same frequency. A 1 kilohertz square wave will have a sine wave at 1 kilohertz and 2 and 3 and so on. Okay. So, similarly, this can be further generalized into any signal being represented as some linear combination of exponentials. Okay. After all, sinusoid is also some exponential, right, with s being imaginary. Okay. So, with those two, you can come up with this generalized analysis of systems, right. For any input, you will be able to find the output using what is known as the Laplace transform. We won't get into it here.
you will see that in another course. Okay.
So, now we have solved the first order circuit for a constant input and for an exponential input. Now, of course, these two are not really separate cases. If I put s equal to 0, I get the other one, right. That is pretty obvious. If I put s equal to 0, this bottom becomes 1 and I have Vp and V naught exponential minus T by RC. Okay. So, a constant is also an exponential with this s is like a frequency, the frequency being 0. Okay. Is this fine? So, just like if you have cos omega t, omega is the frequency of the sinusoid. So, this exponential st, s is like a frequency, right. A large value of s means that the exponential changes very rapidly, whether it is positive or negative. If it is negative, it will decay very rapidly. If it is positive and large, it will blow up very rapidly. Now, if the value of s is very small, again, whether it is positive or negative, it will either decay very slowly or creep up very slowly. Okay. And if s is 0, it will not change at all. Okay. And that is the same with sinusoids also. Cos omega t, omega is 0, it does not change. Is this fine? So, the important thing to take home from here is that now we have done this for a first order linear system, but this is true of any linear system. Okay. So, if we have second order or third order circuits, this will still be true. The particular thing we have found out is for the first order sum.